half wave control rectifier. Yes.
Good afternoon, sir.
Good afternoon. Okay. So last time, okay, we have done single phase half wave converter, okay, with RL load. Okay, we have finished this one and the relationship between the variation of output voltage with respect to delay angle. Okay, we have seen this. Now we have I have asked you to solve these two problems. These two are quite easy. Okay, if you know the formula, you can directly find out. Okay, these two problems. Now even we have talked about single phase half wave converter with RL load. So this we have already done with freewheeling diode. Okay. Now today we look on this half controlled converter bridge type configuration. Okay, in this half control converters means like it can be connected in either arm of the bridge in this type of converters. Okay, and the major advantage of these converters is to increase the average load voltage. So average load voltage in this type of converters bridge type configuration, so output voltage can be increased and improved, and also to improve the power factor. You know the effect of power factor. Okay, if you want to have at least around 0.8 to 0.9%, means like 0.8 to 0.9 power factor. So this will really improve the power factor and also improve the shape of the input current waveform. So these are some of the advantages of using the bridge type configuration, means half control converter, and are used in motor. The application part, it is used in the motor field supplies or the supply direct current to the highly inductive load. So in this case, we can use the bridge type configuration of half control converter. And these are the two different types of control bridge converter with R load. Load can be, we are just taking a typical cases. Okay, we don't, but in practical cases we not have a pure resistive load, that you know this. So there are two different types, symmetrical configuration and asymmetrical configurations. So there are two different type of configurations are there in single phase half control bridge converters with R load. So in symmetrical configuration, okay, you'll find out two thyristors and two diodes are used. So cathodes of the two thyristors have a same potential so that the gate can be connected. So when the cathode of the two thyristors have the same potentials and this is the symmetrical configurations. So these two cathodes of the two thyristors have the same potentials. So this can be connected, cathode can be connected together. So same potentials and that can be connected in a single phase and for triggering other thyristors. So in this case, if the cathodes are connected together, so this triggering can be possible, or both either can be triggered in these cases. So the thyristor which is forward bias at the instant of firing will be turned on. So based on this, whichever is the forward bias, suppose if this thyristor T1 is a forward bias, and this thyristor will be triggered so that there will be a conduction in this case. So from this, so L, T1, R, then D1, then N. So this is the process. So if this becomes a forward bias, then this will be triggered. The output voltage will be improved in this case, and even the power factors. So with input power factor will be improved in this case. But our main focus here is we are converting AC into DC. So you must be thinking that why we are talking about the power factor. But we have to talk in case of input. Input it's AC and output is a DC. So the waveform is shown in the figure. So this is the symmetrical configurations where you have a two thyristors T1 and T2 where the cathodes are connected together, and you have a two diode D1 and D2. So in this case, okay, when during the positive half cycles, T1 and D1 will conduct. So during the positive half cycle, this thyristor T1 and D1 will conduct, and in the forward bias, and when T1 is triggered at the firing angle alpha, so if this T1 is triggered at the firing angle alpha, so then there will be means the current will flow through this path. So this is the path. Path is L, T1. So when it is positive, right? When the positive half, during the positive half cycle, T1 and D1 will be forward bias, and this T1 will be triggered. Then the flow of current will be in this direction, L, T1, R, D1 and N. So this is the flow of the current during the positive half cycle. So the load current will flow until commuted by the reverse supply voltage. So this will keeps on flowing until there is a reverse flow current. So this is the point. So you're triggering at this point, Ig1. So you're triggering this. This is the supply voltage and this is the load voltage. So the output voltage will depend on this firing angle also. So output voltage will depend on this firing angle. So you're firing a pulses to the thyristors. So this portion is the load voltage, and the whole this is the supply voltage. So and the load current is based on this. So it based on this triggering pulses. So this is the firing angle between this. So it's shown as a alpha. So this is the path the way it's flowing in in this case T1 and D1 is conducting. Means highest T1 and D1 is conducting, and this negative half cycle T2 and D2 is conducting. So during the negative half cycle, T2 and D2 are forward bias, and T2 is triggered at an angle pi plus alpha. So T2 is, this is pi, right? Pi plus alpha. So the firing angle will be at pi plus, it will be triggered at pi plus alpha. Pi plus alpha, and then current will flow in this. So in second case, how the current flows? So current will flow from L. So how do you current flows? This it will flow from N, T2, R. Okay, it will flow from N, T2, R, D2 and L. So N, T2, R, D2 and L. N, T2, it will flow from here N, T2, R, D2 and N. But in positive half cycle, it is flowing from L, T1, R, D1 and N. But in this case, it will flow from N to T2 to R, D2 and L. So please remember this, during the positive half cycle, it will flow from N, T2, R, D2 and L. But during the positive half cycle, it will flow from L, T1, R, D1 and N. So this current will continue till the angle 2 pi when the thyristor T2 is turned off. So it will flow to this T2 is turned off till this point. So you have to remember this, how the current flows in this circuit in symmetrical configuration, and you should know this diagram, how what is the means like the flows in a circuit diagram. So this is the flow, the output voltage and output current and the triggering process. So if you want to find out output DC voltage, then similar to 1 by pi alpha to pi. So your integration should be alpha to pi. So this is alpha, so it will be from alpha to pi. So Bm sin omega t d omega t. So you'll get VDC equals to Bm pi 1 plus cos alpha. Then average load current will be IDC will be VDC by R, the resistive load. So you'll get Bm by pi R 1 plus cos alpha. So VDC RMS will be Bm by 2 pi root of pi minus alpha plus 2 alpha by 2. So to find out the RMS DC voltage. So asymmetrical configuration. Okay, what difference can you find out from this? The difference is that in symmetrical configuration, T1 and T2, the cathode of T1 and T2 were connected together. But in asymmetrical configuration, if you see T1 and D2's cathodes are connected together. Now that is the difference in symmetrical configuration and asymmetrical configurations, that the T1 and T2's cathodes are not connected together. Now, in this case also, during positive half cycle, T1 and D1 will conduct. So during the positive half cycle, T1 and D1 are forward bias, and current flows from L, similar L, T1, R, okay, D1 and N. D1 and N. And where T1 will be is triggered. So during this, it will be forward bias. This T1 will be forward bias and T1 will be triggered. So load current will flow until it's commutated by the reverse supply voltage when omega t equals to pi. So when omega t equals to pi, it will flow till this point, from pi to alpha to pi. So when it is triggered at alpha, so it will flow, the output load current, load voltage will be till this point. So even the load current will decrease to, when it is pi, the load current will become 0 at this point, when T1 and D1 is conducting. So negative half cycle T2 and D2 will conduct. This T2 and D2 will conduct during the negative half cycle, and the T2 and D2 are forward biased when omega t equals to pi plus alpha. So when it is pi plus alpha, similar to what we have seen in the previous diagram. So current will flow from N. So it will flow from N, then it will flow in this way. So N, D2, R, T2, and L. So this is the waveform shown here. Similarly, you can find out the average load voltage, VDC equals to 1 by pi, root alpha by pi, Bm sin omega t. So you'll find Bm pi by 1 plus cos alpha. So what is the difference between these two? Bm pi 1 plus cos alpha, right? Bm by pi. So in this sense, also Vm by pi 1 plus cos alpha. The symmetrical configuration of the diodes and the SCR, the placement of the diode and SCRs are different in these two things. So next, with the help with RL load, suppose if you have a load in symmetrical configurations, where the T1 and D2 cathodes are connected together, and the addition here is L load, so inductive loads are there. This is a real practical things, means like our loads can be inductive and it can be resistive, so both the inductive and resistive load will be there. So during the positive half cycle, T1 will turn on the firing, at current IDC flow through L. So similarly, way it will flow through L, T1, K, LD, RL, D, and N. So this is same way what we have seen in that. So similarly, during the negative half cycle, it will flow from here to this way, N, T2, K. Then in this means like in this configurations. So similarly, in this case also, the load voltage will be, this is the load voltage, and this is the supply voltage. Both of this is the supply voltage. And during the positive half cycle, so this is a point where T2 and D1 is conducting, and T1 means T2 means in this one, T2 and D1 is conducting, T1 and D2 is conducting in this case. So this is the load current, inductive. Now this load current is not becoming 0 at this point. So similarly, what we have seen in the half control, this is not becoming 0, but it's going beyond this point. So where it will be pi plus beta, or you can say that it's going beyond this point. So similarly, average DC load voltage, neglecting the diode and thyristor drop, so we can find out VDC will be 1 by pi Bm sin omega t. So VDC will be Bm by pi 1 plus cos alpha. So you might see the similar type of equation in almost all the means like whatever we have seen till now. So average DC voltage will be Bm by pi r 1 plus cos alpha. So a symmetrical configuration with the RL load also. This is a symmetrical configuration which we have seen similar to where the difference is where L load was not there. Similarly, you will have a similar type of waveform in this case also, where this is the output DC means load voltage, and the supply voltage will be, so based on this, so it's triggering at an alpha. So D2 and D1 will be conducting in this case, and in this case T1 and D1 will be conducting, and these portions where D1 and D2 will be conducting in this portion, this when it is alpha at this point when it's triggering. So similarly, we can find out the VDC. VDC is same, and IDC also Bm by pi r 1 plus cos alpha. Now, can we solve this problem? Can you just copy this problem so that we can solve together here? A voltage source of Vs 100 sin 314t supplies a resistive load of 110 ohm through the thyristor, which performs a half wave control rectification. So calculate the average power of the load if the thyristor firing angle is alpha. Alpha equals to 45 degree with respect to supply voltage. So you have to find out the PDC. So before finding out the PDC, you have to find out the VDC. So the rest is the purely resistive load. So VDC will be Vm by 2 root pi. Means how do you find out VDC? Means you have to find out the RMS voltage. VDC RMS voltage. So RMS voltage will be Vm 2 root pi. So can you just copy this question?
VDC 54.338, sir.
Wait, okay. So if you see here, okay, BDC equals to Bm by 2 pi minus alpha. So 47.67, right? So this is how you have to. So VDC means RMS value is equals to Bm by 2 root pi. So it will be root of pi minus alpha plus sine 2 alpha by 2. So you will get VDC RMS value will be equals to 47.67. So it will be 47.67. And if you, once you know this VDC, then V means PDC will be VDC RMS whole square divided by R. So this will be 47.67 whole square divided by what's the value of R? R is 10. So your PDC will be 227.3 watt. So this is direct application of formula. If you know, once you know the RMS value, VRMS, then you can find out with what will be the power delivered to the load. Okay. So this is how we do. So BDC will be 47.67 and PDC is around 227.3 watt. So please do this problem also. It's quite simple. Okay. So you just have to determine the form factor, ripple factor, okay, transformer utilization factor, peak inverse voltage of a thyristor. So you have to assume the turn ratio to be 1:1. Last time, okay, I think it was Ise, okay, she was asking me the how do you convert from primary to secondary voltage. Primary, if you have the turn ratio, it means like transformer ratio is 1:2. So that I feel that you know this, okay, how do you convert this? So please try to, in this case, the transformer turn ratio is equals to unity. So please take this, you don't have to do anything, okay, in this when the turn ratio is just unity. So please solve this problem, okay, and this don't do as assignment, okay, please try to look into this. Actually I have removed the soft copy of the textbook, okay, means like PS Bimra and Rasid, because of some copyright issues, okay, we it's not allowed to upload in any, but if you require these two textbook, I've already forwarded to few of your friends. If you want, you just write me a mail, so I'll forward to you in the mail, so that if you want to go through the textbook, okay, please go through this half control rectifier with RL load, freewheeling diet, okay, circuit diagram, waveform equations, okay, please go through this. You don't have to submit as assignment, but I've given you a few assignment. I know three of you have not submitted this assignment. I've already written a mail to you, so please do it as soon as possible. Because if you do not submit the assignment, I'll directly give 0 in this assignment part. So please be careful. I've already written a mail. I know you must have already looked into these things. So please submit your assignment as soon as possible. So with this, we have completed.
Sir, कति है?
Sir, masih
Sir, गन्दी हो म?
Sorry, okay, there is some problem with the connections, internet connections. Are you able to hear? Yes. Okay. Let's continue with the full control converter. Now, in this case, in half controlled converter has the output voltage is varying from positive maximum to 0, and its operation is only confined only in first quadrant. So you must be knowing there are 4 quadrants. Okay, this in half control converter is confined to only first quadrant, and half control circuits, the input converter has a large DC component. Means like in half control, halfway in circuits, so the input voltage has a large DC component since the current flow is unidirectional. So in this case, the current flow is in only one directions. So it's a half control, so it is positive maximum to 0 only. So only one pulse of load current is produced during the one cycle of source voltage. So it means that it produces only one pulse of the load. So if you see this, is also known as a single phase one pulse converter. That's why there's only one pulse of load current is produced in this. So because of that, it is also known as a single phase one pulse converter also. So half control converter. So these are some of the disadvantages of the half control converters. So to overcome these disadvantages, like disadvantage input converter has a large DC component, and it varies from the positive maximum to 0 only. So it converts only one pulse of load current. So these are some of the disadvantages of half control converters. So with this, so we need to minimize the disadvantage of using this single phase, means like half converters we can use a half single phase full wave converter to overcome this disadvantage. So single phase full wave converters is also known as a single phase 2 pulse converter. If you remember it, single phase half converter is only 1 pulse converter, but single phase full converter is a 2 pulse converter, because there is only 1 pulse produced in this. 1 pulse of load current is there in case of half control. So single phase, there are 2 types. There are 2 different types: single phase full wave midpoint converter M2 connections, and other one is a single phase full wave bridge converter B2 connections. So these are the 2 different type of full wave converters, M2 and B2 connections. So single M2 connections is single phase full wave midpoint converters. So it's made of 2 single phase converters feeding the same load. So it's made of 2 single phase converter, and it is feeding to only one load. So And the converter transformers contain a midpoint secondary voltage. So it also contains a midpoint secondary voltage, and load is connected between the center tape of the secondary winding. So it also has as a common cathode point of two thyristors making of a converter. So please remember that it's made of two single phase converter feeding to the same load. So this is it's a midpoint converters with the R loads. So this is circuit diagram. So there are the cathode of the two thyristors are connected together and is feeding to the same load. So during the positive half cycle, when omega t equals to theta to omega t equals to pi, omega t equals to theta to omega t equals to pi, point A is positive with respect to B. So point A is positive. Okay, when omega t equals to, at this point 0 to pi, point A, this point is positive with respect to point B. And T1 is forward bias. These thyristors, T1 is forward bias in this case. So if the T1 is fired at an angle alpha, so if this T1 is fired at an angle alpha, current would flow through A, T1, R, A, T1, R, and O. So this is the direction of the flow of current. So A, T1, when T1 is conducting, and if T1 is fired, if this A, T1, R, and O. A, T1, R, and O. This current continues to flow to omega t equals to pi. So this current will flow till this pi, from alpha to pi. The output current is flowing in this case from alpha to pi. So this is the waveform. So the voltage, output voltage is also from alpha to pi. So alpha to, so when omega t equals to pi, supply voltage Vs and the load voltage B naught. So supply voltage and load voltage at, so in this case, so it becomes B, this becomes 0 at pi. Vs will be equals to 0 in this case. So current through T1 will be equals to 0. Therefore, thyristor T1, this thyristor will turn off when omega t equals to pi. Thyristor T1, this thyristor will turn off at omega t equals to pi. Turn off by the line or natural commutation. So these two techniques can be used. Line commutations or natural commutation techniques are used to turn off these thyristors. So during the negative half cycle, omega t equals to pi to 2 pi. So omega t equals to pi to 2 pi. So this case at the angle pi plus alpha to 2 pi, this till this point. So point B is positive. So in this case, during a negative half cycle, this is positive with respect to A, or even we can say with respect to O. So positive with respect to point A, T2 is forward bias. So thyristor T2 is forward bias and T2 is fired at an angle. So omega t equals to pi plus alpha. So this is fired at pi plus alpha. So this is thyristor T2 is fired, means it start conducting at pi plus alpha at this point. So it means that T2 is conducting in this case. So output DC voltage is equals to pi plus alpha to 2 pi during the negative half cycle. It means that it's conducting both the half cycles. So T2 is fired at omega t equals to pi. So the current flow will be B T2. It will be from B T2 to this direction. The current will flow from B T2 to R to O. B T2 R and O. So flow up to an angle omega t equals to 2 pi. So at omega t equals to 2 pi, Vs supply voltage in V not load voltage is 0. And the current through T2 will be 0, when means like T2 will stop conducting. So T2 is turned off by the line, and assume that T1 and T2 are triggered at the same firing angle, same square load. They have same shear load, equal load. So it means that these two thyristor T1 and T2 are fired at same angle, firing angle, and they are feeding to this same load. So this is the condition. So you have to remember that both T1 and T2 are triggered at the same firing angle, and hence they share the equal load. So this is the waveform. So this is the voltage in thyristor T2 voltage. across thyristor T2 and the voltage across thyristor T1. So we can find out the average output voltage. VDC will be equals to 1 by pi. So integration will be from alpha to pi. So it will be integration level will be from alpha to this pi. So Bm sin omega t. So you'll get Bm 1 plus cos alpha. So DC voltage also, DC load current will be VDC by R, and RMS will be Bm by root 2 pi minus alpha to sin 2 alpha by 2. So we can find out even RMS current also, BRMS by R. So just if you know the RMS voltage, then if divide by R in purely resistive load, then you can find out IRMS. So this is a simple example. So a single phase full wave control converter is supplied at 220 volt 50 hertz. So you have to determine the average load when the firing angle is 45 degree for purely resistive load. So VDC will be Bm1 plus cos alpha. So you'll find out. So Bm will be so you'll find out the pi 169.05. So you can go through this single phase full wave midpoint converter with RL load and freewheeling diode RLE load. So please, you don't have to go for RLE load, okay, but just do with RL load only. So with freewheeling diode also, because we have already done this with RL load for other cases and a freewheeling diode also. Now this is the previous one is M2. Now this is B2 connections, single phase full wave bridge converters, B2 connections. So in midpoint center tape is used. Midpoint center tape is required. So by using the bridge configuration, we can avoid the transformer requirement. So if we use the bridge configuration, so we don't require a transformer in this case, in B2 connections. It requires the 4 thyristors. If you remember, even in half control converter, there are 2 different types, where one is used for only 2 thyristors and the other one is using a 4 thyristors. So in this is a bridge type converter where 4 thyristors are required. So operate either in first quadrant or fourth quadrant. It can operate in first quadrant as well as in fourth quadrant, and it's also known as a two quadrant converters or fully controlled converter. So this is a 2 quadrant converter or fully 4 thyristors are used. T1, T2, T3, and T4. 4 thyristors are used, and the load is purely resistive load. You can find out the DC output voltage across this load. So during the positive half cycle, T1 and T2 will be forward biased. So T1 and T2 thyristors will be forward biased. And at omega t equals to alpha, firing pulse is given to T1 and T2. So it means these two are fired together. It means the two are conducting together. So current flows through PH. Okay, PH. Then T1, A, R. So this is PST, A, R, B, T2, and N. So this is the flow of the current. PS, T1, A, R, B, T2, and N. PS, T1, A, R, B, T2, and N. So at omega t, supply voltage and load voltage will become equals to 0. In this case, if you see at this point, DC output, I mean, this is the current. Okay. So even DC means DC voltage, this is the voltage. So at omega t equals to pi, VDC is equals to 0, and even IDC is equals to 0. So instant when omega t equals to 2 pi, the supply voltage will reverse, and in this case, T3 and T4 will start conducting. These two thyristors will start conducting during the negative half cycles. So turn off. So this one will be the supply voltage reverse and thyristor T1 are turned off by the line commutations. Means this T3 and T4 are forward biased. So omega t equals alpha by plus pi. The firing givens are T3 and T4. So current will flow from N. So this is the K. So this is in this way it will flow to NT3. So NT3, A, R, B, T4, and PH. So this PH. So it will flow in this way. N, T3, A, R, B, T4, and PH. So again, this when it is reverse bias, when omega t equals to 2 pi, T3 and T4 will turn off. And similarly, the interval will omega t will be alpha plus pi. 2 omega t load voltage and source voltage. So load voltage will be equals to source voltage because the load is directly connected to the source. Load is directly connected to the source. In this case, this load is connected to this source. So connected to the source through T3 and T4. So this is the waveform. So please look at this waveform. Okay, in this case, during the positive half cycle, thyristor T1 and T2 is fired. That's why get current IG1 and IG2. So this is firing at during the positive half cycle. So during the negative half cycle, thyristor T3 and T4 is fired. So it means that get current IG3 and IG4 are given here. So this is the output voltage, DC output voltage during the positive half cycle. The output DC voltage is alpha to pi. So during the negative half cycle, pi plus alpha to 2 pi. So this is similar to this voltage and output DC voltage and output DC current can be seen through this. So what is the thyristor voltage across the thyristor T1? So we can even find out when thyristor is not conducting, it means that there is a certain rise in the voltage in thyristor T1. So similarly, we can have the voltage across thyristor T2, T3 also. So we can find out the average output voltage. VDC will be 1 by pi. So integration will be alpha to pi. Bm sin omega t d omega t. So we can find out Bm by pi. This is same as what we have been seeing this IDC also. Bm pi plus pi R1 plus cos alpha. So RMS also, this is the same thing which we have seen in the previous one. So we can even find out the RF current. So this is the problem related to this. So 240 volt, 5 kilowatt resistive load is connected across the fully controlled single phase bridge converter. So this is the bridge converter, single phase full control bridge converter. So what you have to find out is if the load is to be delivered, a power of 1000 watt, then if power of 1000 watt, then you have to find out the output voltage and RMS value of the load current. So if you know the formula VRMS will be, you can find out from this. So VRMS can be 107.33 volts. So please try to do these problems. Like all these problems are, if you know the formulas, you just application of the formulas. So you can even do for the RL load. Okay. You don't have to do with the RLE load. This RLE load you don't have to do, but with RL load, please do it circuit diagram and waveform and try to see try to find out the average DC voltage, RMS voltage, okay, and compare the full control bridge rectifier and half control bridge rectifier. So what is the difference between the full control bridge rectifier and the half bridge control rectifier? So please try to do the comparative study. It's there in the textbook. If you have PS Bimra, this comparison is clearly written in the tabular form. So please go through this comparison. So what is the effect of the source impedance on the performance of the converter? So what is the effect of the source impedance on the performance of So this source impedance, it has the effect on the performance of the converter. So input source impedance is important for input transformer or for the load impedance connected to the converter. So impedance are normally predominantly inductive. So impedance it means like it is most of the time is inductive in nature, and impedance of the fully controlled bridge converters is shown below. So this is what is the effect of the impedance? This is the source impedance of the fully controlled bridge rectifier. So what is the effect of this source impedance on the performance of this converter? So if the source impedance is purely resistive, then the commutation of the thyristor may be considered as instantaneous. But if purely inductive and a large process of, I think the equation equal to sign is not there. So purely inductive and large process of commutation of the current from one thyristor to the other is modified. Commutation process is modified. Okay, there is some mistake on this. So commutation process may take some time. So in this case, okay, because if there is a source impedance, means like purely inductive and a large process means like in commutation there will be like commutation process may take some time if there is because of the source impedance. So during both the incoming and outgoing thyristors conduct simultaneously. It means that incoming and outgoing, both the thyristors are conducting together. So you have 4 thyristors, right? So these thyristors are, suppose in a positive half cycle, T1 and T2 should conduct. During the negative half cycle, T3, and because of the source impedance, purely inductive in nature source impedance, so it might means like both the thyristors might conduct simultaneously. So this period is called overlapping period. So how do you say? Means like it's something like, I don't know. I have been talking about this. Okay, that lapping, overlapping, something like a crossover. If you have means if you have remembered, I think in analog electronics, somewhere in power amplifier, somewhere there in this push-pull amplifier, there is something like crossover distortion is there. It means that there is some problem. Means it that both there is some overlapping. Means like both the actually when one thyristor stop conducting, others should start conducting. But what happens if there is a source impedance? It both the thyristors are simultaneously conducting. Means like it does not stop conducting. Okay, when another thyristor is conducting. But if there is a source impedance, it means that both the incoming and outgoing thyristors is conducting simultaneously. So there is something like overlapping. In terms of a communication point of view, we call as a crossover. It means that you are hearing somebody else when you talk with your friend. You are hearing that voice of somebody else when you talk with your friend. So that is something called as a crossover. Crossover means that you're hearing somebody else's voice. So similar to this, even in this case, means that when one thyristor should stop conducting, when other thyristor start conducting. So, but this is not happening when there is a source impedance. When there is the impedance at the source. So because of that, there is a problem on that. That problem is like it's overlapping. Means that 2 things are going simultaneously. But in reality, it should be only one thing should work, and other things should stop. It means one thyristor should conduct and others should be stopping. So that overlapping is commutation overlapping is going on. So this is the circuit diagram of. So the equivalent circuit diagram, if you try to draw the equivalency of this circuit, so you'll get in this case, in this way. You have a 2 thyristors T1 and T2. Thyristors T1 and T2 are conducting, and T3 and T4 are conducting negative half cycle. So we can draw these are the 2 source inductance. So source impedance are there, LS are the 2 source impedance. If you see here, so there is a overlapping. So this overlapping is going on. Current and voltage waveform. This is V1 and V2. Okay, then it's triggering simultaneously actually. So triggering T1, thyristor T1 and T2 as triggers at this point, and another one T3 and T4 are triggered in this one. But what is happening is that there is certain overlapping going on. It's still T1 and T2, T3 and T4. There is that all these thyristors are conducting at this overlapping angle. So because this is happening all because of this source impedance. So this is the effect of source impedance on the performance of a converter actually. So during the positive half current part will be PH L LST1. So you can just go through this. Okay, how the currents in during the negative half cycle and T3 load PS. So this is the way how the currents are flowing, similar to what we have seen in the previous case. So initially assume that these two thyristors, that T4 and T3 and T4 pairs is conducting, and when T1, so we have to assume that T3 and T4 are conducting. So T3, and we have to assume that initially these 2 thyristors, T3 and T4 are conducting, and T1 and T2 are triggered at the firing angle alpha. So these two T3 and T4 are already conducting. We have to just assume this. So we have these two thyristors are conducting. So current increases slowly from 0 due to the source impedance and transferring this current from T3 to T4 pairs. So it is conducting. So current is slowly increasing. So this is the current. So current is slowly increasing. So initially we have assumed that T3 and T4 are conducting. Now current is slowly increasing on this. So slowly, now again T3 and T4 slowly decreases to 0 from its initial value IGC. So at the same time, incoming thyristor T1 and T2 built up gradually to full value of load current IGC. So it is gradually developing to full value of IGC. So in this case, T1 and T2 are conducting. Actually, to be like precise, okay, this is the voltage. Voltage is conducting till this. So at this point, at omega t equals to pi, voltage is becoming 0, but this current is not becoming 0. It's going beyond this point. So gradually, to these changes take place due to the overlap period. This omega overlap angle mu. So this is the overlap angle that there will be overlapping, which is known as overlap angle is equals to mu. So it means that there is a overlapping between. I think overlapping angle is not shown in this case. So there is a overlapping in this angle, the angle which is overlapping with when both the thyristors are conducting. So that angle is known as overlapping angle mu. So as all the thyristors are conducting during this period, Vs is absent and VL equals to load voltage equals to 0. So this overlapping period, this is actually overlapping mu. This is the angle. So voltage is equals to V, load voltage is equals to 0 at this point. If you see here in the waveform, this portion is equals to 0. So from it's clear that a part of the load voltage is lost, which would otherwise be present if there is no source inductance. So if there is no source inductance, this voltage might not be equals to 0 at this point. But because of the source impedance, this voltage at this point, when there is a overlapping angle mu, this at this point the load voltage is equals to 0. But if there were no load voltage, then this would have been not been equals to 0. So during the overlap angle mu, KVL of the loop Q, so we can find out this. So V1 minus Ls. So with this, we'll find out that V1 minus V2 will be L D1. How do you find out V1 and V2 in this case? So we can find out this. So L di by dt. So when the load, when it is inductive, okay, source impedance, these are the inductive in nature. So L equals to di by dt. So V1 minus Ls di by dt equals to V2 minus Ls it2 by dt. So if you solve this, you'll get Ls equals to d1 to d2. So similarly, you will get v1 equals to bm sine omega t and v2 equals to minus bm sine omega t. So if you replace with this on these equations, v1 and v2, with v1 equals to sine omega t and v2 equals to minus bm sine omega t, then you'll see this 2 bm sine omega t. So 2 bm sine omega t equals to Ls di by dt, which we have found. So if you assume the load current is constant, IT1 and IT2 equals to IGC, then we'll find out this equals to 0. So in adding equation number 2 and 3, if you in this one 2 bm by Ls sine omega t, then if you add this equation, then you will get dit1 by dt will be bm Ls sine omega t. So during the overlapping period, load current IT builds up from 0 to IGC through has a T1 and T2. So omega t will be equals to pi. So during initially period, omega t equals to pi. So at this point, so omega t equals to pi, IT1 will be current through the thyristor T1 will be equals to 0 and omega t will be equals to alpha plus mu. This is the overlapping angle, alpha plus mu. This is alpha, and this is the overlapping. This is the mu. So this portion between this portion, this is alpha. This portion is alpha, alpha plus mu. Mu and IT1 will be equals to IGC. So if you try to integrate this, you will get the IGC will be Bm omega Ls cos alpha minus cos alpha plus mu. Mu is the overlap angle. So even we can find out the DC voltage. So all this all this IDC, VDC, okay, we are finding if there is a source impedance. So we are just seeing that what is the effect of the source impedance on the overall performance of the converter. So if there is a source impedance, if there is no source impedance, if you do not take care of the source impedance, it's quite simple. But if you take a source impedance as an inductive source, then what is the effect overall performance on the inverter? So we can find out the VDC also with similar way. Again, with from the equation number 5, we can find out that cos alpha equals to cos alpha plus mu. So omega ls by Bm IDC. So using this value of equation, we can find out VDC equals to. So please go through this and try to solve for yourself. Okay, before looking at this, try to understand this, because what we are just trying to use this means the inductive nature of the source impedance. So if there is inductive nature of the source impedance, what is the overall means like output? So with the help of this equation, DC equivalent circuit can be drawn. So we can draw the equivalent circuit when there is a source impedance. So 2 Vm by pi cos alpha. So this is the source. So we have a diode D and omega ls by pi. So and this is the load voltage and load current. Diode indicates the load current is unidirectional. So it means that this diode is indicating that the load current is in unidirectional. The voltage drop due to the source impedance Ls in proportional to IDC and L. So there is a drop in the voltage. So thus, as the load current increases, the commutation interval increases, and the result average output voltage will decrease. So it means that average output voltage will decrease in this case. So output voltage, okay, if you see this is the slope. So as if when this is increasing, right, this slope you are drawing the average, this load voltage is decreasing. So if the current will keep on increasing, suppose this is the current. So if the current will keep on increasing, if you have to draw the slope in this way. So this clearly shows that load current increases and increases, the commutation interval increases, and as the result, average output voltage will decrease. So voltage will keep on decreasing. So with the help of this, you can find out you have to find out the single phase full control bridge converter has supply voltage 230 volt and 50 hertz with the source inductance of 2 millihenry, 2 mH, and determine the load voltage neglecting the resistance voltage drop. So you have to consider now there is the source inductance equals to 2 mH. So you have to find out what is the key. Then what is the converter is operating at the firing angle of 45 degree. So if the converter is operating at a 45 alpha equals to 45 degree and the load current is constant at 10 ampere. So what will be you have to determine the load voltage. So we can just use the formula VDC equals to 2 Bm pi cos alpha minus omega ls by pi IDC. So you can find out VDC with, if you remember the formula. So we can find out VDC equals to, in this case, mu equals to 6.31, the angle between this overlapping angle. Then the load resistance will be VDC by IDC. You can find out the load R also. Similarly, in this one, okay, if you have a single phase full converter is connected to the AC supply of 330 sine 314 T volt and 50 hertz, it operates at the firing angle is alpha equals to 45 degree. And if the load current is maintained constant at 5 amperes, if the IDC is equals to 5 ampere and the load voltage is VDC is equals to 140, you have to find out what is the source inductance L, and you have to find out also mu, angle of overlap, and the load resistance. I think this one is already solved here. So VDC, if you know the formula, with the help of this formula, you can find out LS. So all this, whatever is there in the PPT, it's all taken from the Rashid. Most of these things are taken from Rashid and Bimra and Subramaniam. If you have these two textbooks, it's more than sufficient. And I have already circulated these two textbooks to you. Even if you do not have a hard copy, soft copy is with you, the PS Bimra and Rashid. So these two textbooks are already with you. So if please try to solve this problem. So if you face anything, we'll discuss in next class. Is it okay? Yes.
Yes, sir.
I'll just check.
Sorry, sir.
Wait, okay, I'll just take attendance. Okay, please try to solve this problem, whatever is there in the PPT. Okay, so please try to solve this problem. I'll try to, if it's possible, I'll try to give you more problems, okay, as a tutorial. So please try to solve this problem. If you face anything, okay, we'll discuss in next class, okay, especially with the full single phase full converter and even for the half converter with both R load, RL load. Most of these formulas are similar type of formulas are there. So if you know the formula, you can directly apply the formulas. So it's quite means you have to remember this formula and you should know how to like do the derivation, little bit of derivation is just to do the integration part only. So with this, I'll stop here. So we'll continue our class tomorrow. Tomorrow we don't have, I think day after tomorrow, right? So tomorrow also we have a class, 9:30 to 10:30. Okay,
Yes.
then I'll stop here. Okay, bye.
Thank you, sir.